Hi everyone, this is Xiluo, and today I'm going to talk about HAN, a hierarchical auto-tuned collective communication framework. MPI stands for Message Passing Interface. It is a standard to specify the communication between processes. MPI is widely used in the HPC community. There are many MPI implementations of the MPI standard. This work is based on Open MPI, one of the open source MPI implementations, and focuses on improving the performance of MPI collective operations. Collective operations are the communication pattern involve multiple processes. Based on previous research, their performance can directly impact the performance of applications. There are many factors could impact the performance of MPI collective operations. An MPI collective module needs to utilize the hardware specifications and topologies to achieve good performance. For example, traditional tree-based algorithms are suboptimal for intra-node collective operations as they introduce extra memory copies. If we can utilize the shared memory space to exchange data across processes on the same node, the number of the memory copies can be reduced. The graph on the right side shows the performance comparison between a specialized shared memory collective module and the default Open MPI module on MPI broadcast. We can say by reducing half of the memory copies, the shared memory module achieves 2 times speedup. The same hardware-aware design goes for the internal level. Collective operations need to leverage the full duplex mode of interconnects, which means the communication on the exact opposite direction can happen at the same time to maximize the network bandwidth. Another important factor of the performance of collective operations is the configurations of a collective communication framework. There are many algorithms for each collective operation, and they have various performance characteristics and are suitable for different situations. This suggests we need to have a way to choose the best algorithm for different situations. We also need to carefully select the segment size for big messages to balance the segment size and the number of segments. There are some other factors, such as underlying P2P performance, could also impact the performance of MPI collective operations. In this paper, we focus on the first two factors, the hardware specification and topologies, and the configurations of the collective communication framework to improve the performance of collective operations by providing HAN. At first, I will talk about how to utilize the hardware specifications and topologies with a hierarchical approach. A hierarchical collective operation is usually implemented as a combination of multiple fine-grained collective operations, where each of them handles the communication on one hierarchical level. There are some factors that need to be considered when implementing a well-performing hierarchical collective communication framework. First, on each level of the hierarchy, the algorithms of the fine-grained collective operations need to fully explore the hardware capabilities. Second, a well-designed hierarchical collective communication framework should maximize the communication overlap, especially for large messages. Last, facing the fast-changing hardware, a hierarchical collective framework needs to be flexible enough to adapt to new architectures. The design of HAN addresses these challenges. First, it selects the proper collective frameworks as submodules to utilize the hardware capabilities of each level. Currently, we use MPI split type to divide collective operations into two levels, internode and intranode. And we select suitable existing collective modules in Open MPI as submodules for each level. Second, the design of HAN adopts a pipelining technique to overlap communications. Finally, due to Hand's modularized design, it can easily switch out submodules to adapt to hardware updates. Overall, our Hand framework breaks a hierarchical collective operation into a sequence of smaller collective communication patterns, or tasks, with each task containing fine-grained collective operations. These fine-grained collective operations are selected from available submodules to utilize the hardware capabilities of the intra and internal level and overlap communications on these levels. These two graphs show the design of MPI broadcasts in Hand. In the internode level, each node selects one process as node leader to exchange messages across nodes, while in the intranode level, all the processes participate in their local communications. On node leader processes, each segment needs to go through 2 steps to reach a destination. An internode broadcast shown as IB here, followed by an intranode broadcast shown as SB here. S stands for shared memory. So at iteration 0, the needed task is IB0, which issues an internode broadcast for segment 0. At iteration 1, the needed task is SB-IB1, which issues a shared memory broadcast on segment 0 and an internode broadcast on segment 1. We consider the cost of a collective operation to be the longest time among all the processes. This definition has been used by multiple cost models. We compute the cost of MPI broadcasts by aggregating the cost of tasks at each iteration in the figure. So the time spent in node leaders is this, and the time spent in other processes is this. So where U is the total number of segments, and TI IB0 means the duration or cost of task IB0 on process I. Usually, the cost of SB-IBX is larger than SBX, since it has an actual internode broadcast to do. Therefore, comparing these two equations, we use the time spent in node leader processes as a cost of MPI broadcast. Once we have the cost model, the next job is to get the cost of each task in this equation. Since IB0 is the first task, we assume each process issues it simultaneously. Hence, its cost can easily be measured by a simple benchmark using a loop around a timed task. The last task SBU-1 only contains an intranode broadcast, which is independent of the processes on the other nodes. Since the segment size is the same among all segments, we use the cost of SB0 to represent the cost of SBU-1, and the result is shown as the orange bars in the right figure. The total cost of SB-IB tasks contributes to the major cost of MPI broadcast when U is big enough. To get an accurate estimation of this part, 2 essential factors need to be considered. The first factor is the overlap of IB and SB. IB mainly operates on the interconnects between nodes, while SB communicates over the memory bus, which means these two broadcasts can overlap to some degree. If the task IB and SB can overlap perfectly, then the cost of SB-IB should be equal to the maximum cost of task SB and IB. However, the overlap may not be perfect because of the 2 following reasons. 1, IB needs to push the data back to the memory, which compete with SB for the memory bus. 2, in single-threaded MPI, IB and SB share the same CPU to progress, which affects the performance of both when they are running simultaneously. Therefore, the overlap between IB and SB is significant, but usually not perfect. The second factor is the starting time of SB-IB on each node leader process. The cost of IB0 in the right figure show node leader processes finish IB0 at different time steps, resulting in different starting time of the following SB-IB. To accurately measure SB-IB1, we need to delay the participation of each process by the duration of IB0 step to simulate the different starting time of SB-IB1, and the results of the new benchmark is shown as the red bars in the right figure. The performance difference between the red bars and the green bars prove the importance of considering previous tasks, since the only difference between these two is whether there is an IB0 before timing SB-IB. However, it is hard to accurately get the sum of the cost of task SB-IBs easily. To get the cost of SB-IBI, all previous tasks from IB0, SB-IB1 to SB-IBI-1 need to be executed, which is highly expensive and contains a lot of redundant tasks. To reduce the redundant tasks, we start to look at the performance trend of the IB-SB tasks. The right figure shows the cost of SB-IBI with different algorithms and submodules on a node leader. All subfigures shows a similar trend that after the first few tasks, the cost of SB-IB is stabilized. It is because when executing the first few SB-IB tasks, the pipeline of the tasks is not fully constructed, leading to some delays. Once the pipeline is fully constructed, the cost of SB-IB becomes stable. Hence, instead of benchmarking all SB-IBs, we use the stabilized cost, SB-IBs times U-1, to estimate the total cost of SB-IBs. Therefore, the cost model becomes this. This figure shows the comparison of the estimated time calculated from the cost model and the actual time of doing a full MB MPI broadcast with different combinations of submodules, algorithms, and segment sizes. In some cases, because of the inaccurate estimation of the stabilized cost of SB-IBs, the prediction is not that accurate. However, as seen in the figure, the cost model is accurate in most cases. Comparing to the cost of MPI broadcast across all configurations, we can say that the optimal configuration of either estimated or actual cost, the lowest red bar and the blue bar, are the same. The design of MPI reduce in hand is similar to MPI broadcast. In the implementation of MPI reduce, collective operations overlap even within the same level. For example, internode reduce and internode broadcast can overlap if their communications occupy opposite directions of the same internode network. This graph suggests the estimation of our cost model and the actual performance matches well, and the best configuration funded by both are the same. Next, I will discuss the auto-tuning component in HAN, which is used to find good configurations of HAN and ensure its performance. Existing auto-tuning approaches can be categorized around two methods. The first method is benchmarking all possible configurations of a collective operation. This approach has the potential to guarantee the optimal configuration, but it is extremely costly. The second method is using cost models to estimate the time of collective operations and select the configuration based on the estimations. Instead of directly measuring the cost of whole collective operations, this method only benchmarks a few network specifications, such as gap, bandwidth, and latency, drastically reducing the cost of auto-tuning. However, as stated in many previous studies, cost models are not accurate enough to find the best configuration. Our approach is a combination of the two existing approaches. Our approach utilizes a cost model, but instead of relying on network specifications, our cost model is based on benchmarking of tasks. Compared to the first method, since we only benchmark tasks instead of the whole collective operation, our method can reduce the search space significantly. Compared to the second method, our model improves the accuracy since it considers more factors. Assuming the sizes of the search space of message sizes, segment sizes, number of nodes, processes per node, and the number of available algorithms are M, S, N, P, and A respectively. So the whole time space of using exhaustive search is M times S times N times P times A. Thanks to the task-based design of Han, instead of benchmarking a whole collective operation, we only need to benchmark tasks. As tasks operate on one segment, the search space needed for one type of task are S, N, P, and A. Suppose there are T type of tasks, 3 for MPI broadcast and 8 for MPI reduce. Therefore, the size of the whole search space of our approaches become T times S times N times P times A. For different message sizes, the cost of tasks is reduced. Therefore, compared to the previous approach, Han can reduce M, one of the largest search space, to a constant T. The red bars shows the auto-tuning time using our cost model. It suggests our auto-tuning component reduces the tuning time by 77% as compared to the exhaustive search. Even though with much less auto-tuning time, our approach can still find good configurations. The red bars in this figure shows the performance of MPI broadcast and MPI reduce obtained by our auto-tuning method, which is exactly the same as the best results of exhaustive search, indicating our approaches produce a similar accuracy as the exhaustive search. Previous studies suggest that heuristic is an effective way to reduce the search space. In Han, we use some heuristics to limit the selections of submodules and algorithms. The blue bars in the figure shows the auto-tuning time of the heuristic method, which is only 27% of the original exhaustive search. These heuristics can be combined with our cost model on the benchmarking of tasks to further reduce the search space. The cost of the combined approach is shown as the green bars in this figure and only takes 4.3% time of the exhaustive search. However, by using the heuristics, we are making assumptions to narrow down the search space, which might result in lower accuracy. The blue and green bars in this figure show the results of applying the same heuristics to the exhaustive search and our approach, and indicated that adding heuristics produced less accurate results compared to the original approaches. We evaluated Han on two supercomputers, Shaheen-2 and Stampede-2. We used Intel MPI benchmark to test MPI broadcast and MPI reduce on 4K processors on Shaheen-2. The results suggest that the auto-tuned Han achieves significant speedup against default Open MPI, and it is faster than Korean MPI for large messages. We also use two applications, ASP and Harvard, to compare Han with other MPI implementations. These experiments are performed with 1.K processors on Stampede-2, both indicating that Han achieves decent speedups against state-of-the-art MPI implementations.